this video, we're going to talk about how to balance redox reactions. And to start with, we're going to consider how to balance redox reactions in acidic conditions. And then in a later video, we'll talk about how we have to change our approach when we're in basic conditions. So a lot of redox reactions are not easy to balance using the simple inspection method we've been using to this point. And in particular, what makes it hard is sometimes we need to add H+ ions, hydroxide ions, or waters that don't even appear in the unbalanced equation that we're given. As an example, here we have an unbalanced redox reaction, and then you can see what the balanced reaction looks like here. And so we've got some big coefficients, and also we've got H+ and waters that didn't even appear in our original equation. So clearly, the methods that we've been using to balance equations up to this point isn't going to work for this particular reaction and a lot of other redox reactions. But it turns out it's not that bad. And by far, the easiest way to balance complex redox reactions is using what's called the half reaction method. And so in the rest of this video, we'll be introduced to and then practice this half reaction method for balancing redox reactions. All right, so what we have here is a list of the rules for balancing redox reactions. And I know this looks a little overwhelming at first, but I think once we apply this to a couple examples, you'll start to see how it works, and it won't seem so bad. And so I'm not going to go through and read all these. We'll apply them to different examples. But what you might want to do is either take a screenshot of this or write these down, or if you're taking my class, these are posted on the course site. But have a copy of this out as we do some of these next examples, and so you can follow along with these written out rules as I go through the process. Okay, let's start with a fairly straightforward example. So I want to balance this redox reaction, and before I get into the method where we have all those rules from the previous slide, let's see how our inspection approach isn't going to work for this. Right, so if I just try to do this by inspection, I say, okay, I've got one lithium on both sides, I've got two chlorines on the reactant side, so to balance it, I need to put a 2 in front of the Cl-. Now, the problem with this is, while the atoms are balanced, another thing that must be balanced is the charges. The charges don't have to be 0 on both sides, but the charge on the reactant side must be equal to the charge on the product side. And right now, the charge on the reactant side, both the lithium and chlorine are 0, so I have a 0 total charge on the reactant side, and I have 1 positive lithium and 2 negative chlorines on the product side, and so that adds up to be -1 charge on the product side. So the charges on both sides aren't equal, so my chemical reaction is not balanced. So let's start over and let's use the half reaction method. So go ahead and get out the list of rules from the previous slide. And so if you look at those rules, the first thing that we need to do is assign oxidation states to every atom in our unbalanced equation. And so I'm going to go through assigning these oxidation states pretty quickly. If you're not sure how I'm getting these, you may want to go back and look at my video on how to assign oxidation states. So the lithium here is 0, each chlorine there is 0, the lithium is +1 there, and the chlorine is -1 there. And so we can see that lithium went from 0 to +1, so the lithium was oxidized, and the chlorine went from 0 to -1, so the chlorine was reduced. So the next thing we want to do is we want to separate our overall reaction into half reactions. So the element that was oxidized, the lithium in this case, I need to take the lithium-containing compound on the reactants and the lithium-containing compound on the products, and we're going to separate those from everybody else. And so my oxidation half reaction is going to be Li goes to Li+. And I would recommend it when you're going through this half reaction method, I leave off the states. We can put them back in when we get the final answer, but carrying the states through the whole process could be a little tedious. All right, and so then the chlorine was reduced. So I want to take the chlorine-containing compounds and the reactants and the products, and that will make up my reduction half reaction. And so I have Cl2 going to Cl minus. So now what we're going to do is we're going to balance each half reaction individually, and then we're going to add them back together. And so if we look at the rules, we're on the third step now, and so we want to balance each half reaction with respect to mass. So the first thing we want to do is balance anything that's not oxygen or hydrogen. So in my first half reaction, I've got 1 lithium and 1 lithium, so that's good. In the second half reaction, I have 2 chlorines on the reactant side, so I need to put a 2 in front of the Cl minus. And so now we would say that each half reaction is balanced by mass. If I had oxygens and hydrogens, there would have been some extra steps. That's not an issue here, but we'll see how that works in the next example. Alright, so now I'm on step 4. I need to balance the charge of each half reaction by adding electrons. And so if I look at that first half reaction, I have a 0 charge on the reactant side, I have a positive 1 charge on the product side. And so if I'm adding electrons, since electrons are negative, whatever side I add them to, it's going to make it more negative. So I need to add the electrons to the more positive side. So in this case, if I add electrons to the right, I'm trying to get it to go from positive 1 to 0 so it matches the reactants. And so to do that, I need to add 1 electron. Right? And now the charge on the reactant side is still 0. And now the charge on the product side is the +1 cancels with the -1. And so now the charge on the product side is 0. So that half reaction is now balanced. Now I'll do the same thing for the reduction half reaction involving chlorine. In this case, I have a 0 on the reactant side, 2 times -1, so I have a -2 on the product side. So I need to make both sides equal to the most negative side, right? So I've got -2 and 0. So what I need to do is add 2 electrons to the reactant side, and now the charge on the reactant side is 2 times -1, it's -2. Charge on the product side, 2 times -1, it's -2. And so that half reaction is balanced. And another thing that will always happen, you'll add the electrons will always be added to the product side on the oxidation half reaction, and the reactions will always be added to the reactant side in the reduction half reaction. Now you don't have to memorize that. In fact, I don't even think about that when I'm doing these problems, right? I just add the electrons to whichever side I need to add them to so that the charge is balanced. But what I do always check is the electrons should be added to opposite sides. If I added them both to the products, or if I added them both to the reactants, I know that I've done something wrong. Okay. So now what we need to do, when I add these 2 half reactions back together, the electrons need to cancel. And right now, if I just added them back together, I'd have 2 electrons on the reactant side and 1 electron on the product side, and so the electrons aren't all going to cancel. So what we need to do in step 5 is multiply the entire half reactions by whatever small integers we need to use so that the electrons on the reactant side will be equal to the electrons on the product side in the 2 half reactions. And so what I want to do in this case is I have 2 electrons on the reactant side in the reduction half reaction. I need to multiply this first half reaction, the whole reaction, by 2. Right, so now I have 2 lithiums going to 2 Li+, and then the important part is now I have 2 electrons on the product side. So then finally, we want to add these 2 half reactions back together. So I'll take everything on the reactant side, and those will be my new reactants, and then everything on the product side will be my new products. And so when I put these 2 back together, I'm going to have Alright, and then our final step is to cancel out the electrons. If the electrons don't cancel out, then we've done something wrong. And then anything else that's identical on both sides, and this is generally going to be H pluses and waters, which we didn't have to deal with here, but we will in other examples, we would cancel those. But in this case, the only thing that cancels is the 2 electrons, right? And this may be obvious, but Li is not the same thing as Li plus, so those would not cancel. All right, and so then what I'm left with, I'll go ahead and put the states back in. So I have Cl2 gas plus 2 Li solid goes to 2 Li plus aqueous plus 2 Cl minus aqueous. All right, and then it's always good to double check, make sure it is in fact balanced. And so I have 2 chlorines and 2 chlorines, 2 lithiums and 2 lithiums. The charge on the reactant side is 0. The charge on the product side, I have plus 2 and minus 2, so the charge on the product side is 0. So my my redox reaction is balanced. All right, on the next slide, we'll look at another example that gets a little bit more challenging. All right, so now we want to balance this half reaction, and we're going to use the same set of rules that we did before. So step 1, assign oxidation states to every atom in my unbalanced reaction. So I'm going to have 0, minus 2 for the oxygen. That means manganese is plus 7. The silver here is plus 1. Now the manganese is plus 4, and the oxygen is minus 2. So I can see the thing that was oxidized is the silver. It went from 0 to positive 1. So my oxidation half reaction is going to be involving silver. So I've got, try that again. All right, and then manganese was reduced. The manganese went from plus 7 to plus 4. So the manganese-containing compounds will make up my reduction half reaction. So I have all right, now I want to balance each half reaction by mass. So I want the atoms to come out the same. So for the oxidation half reaction, I think we're good. 1 silver, 1 silver. For the reduction half reaction, the manganese look good. I've got 1 manganese on the left, 1 manganese on the right. So then to balance the oxygens, and this is what we didn't have to do before, to balance oxygens, if we look at step 3, part 2, we balance oxygens by adding waters. Right? And each water will contribute 1 oxygen to whatever side we add it to. So right now I have 4 oxygens on the reactant side, 2 oxygens on the product side. So I need to add 2 more oxygens to the product side. So I'm going to do plus 2 H2O. And now I have 4 oxygens on both sides. So then if we look at step 3, part 3, we balance the hydrogens by adding H+. So I have no hydrogens on this side. I have 2 times 2, 4 hydrogens on this side. So to balance the hydrogens, I'll add 4 H pluses to the left. All right. Now what we need to do is add or balance the charges by adding electrons. So in my first oxidation half reaction, I've got 0 on the left plus 1 on the right. So I need to add 1 electron to the left, or I'm sorry, to the right-hand side. So now both sides are 0. And then in the reduction half reaction, so I've got a charge of the total charge. On the reactant side, I have plus 4 and minus 1. So that means the total charge is plus 3. The total charge on this side, I've got 0 and 0. So the total charge is 0. So that means I need to add 3 electrons to the reactant side. All right. Now, each half reaction is balanced, but before I add them back together, I need to be sure that when I add them back together, the electrons will cancel. Since I have 3 electrons on the reactant side here, and only 1 electron on the product side here, I need to multiply that whole first half reaction, sorry, let's use the right color, by 3. So 3Ag goes to 3Ag plus 3 electrons. All right, and so now when I add them together, I'm going to have 3 electrons plus 4H plus MnO4 minus, and then the 3 silvers from the first half reaction will make 3Ag plus 3 electrons, MnO2, and finally 2 H2Os. Alright, so I think the only thing here that cancels is going to be the electrons. And so then our balanced redox reaction will be 4H plus aqueous aqueous permanganate ion, 3 silver atoms will make 3 silver ions, manganese 4 oxide, and 2 waters. Alright, the last step, let's double check and make sure everything is in fact balanced. I have 4 hydrogens, 2 times 2, 4 hydrogens, 1 manganese, 1 manganese. I have 4 oxygens, and 2 plus 2 is 4 oxygens. I have 3 silvers and 3 silvers. All right, and then when I check the charges, I have plus 4 and minus 1, so the charge on the reactant side is plus 3. On the product side, I have 3 times plus 1 and some zeros, so the charge on the products is plus 3. So the charges are equal on both sides, and so this is my balanced half reaction. All right, so I have one more example of balancing redox reactions in acidic conditions that's a little bit more challenging still, but this video got kind of long, so I have that in a separate video.